1 molal. In theory, though, theoretically anyways, according to the balanced chemical equation, when you dissolve magnesium sulfate in water, or when you allow the magnesium sulfate salt to dissociate, those ions to dissociate in water, you end up with 2 moles of ions per kilogram of water. So in that mass, you would end up with 2 moles of ions. And let me show you how that happens. So if we draw out magnesium sulfate, so magnesium typically takes on a positive 2 charge, and we know that sulfate has a negative 2 charge. So these guys come together in 1-to-1 ratio, right? And if we have that as a solid on the reactant side, and we put this into solution, so we're going to allow this to dissociate into, say, a kilogram of water, 1 mole of that salt, right, as we're writing this reaction equation. What ends up happening is, theoretically, the salt will dissociate into its constituent ions, and you get magnesium 2 plus and sulfate 2 minus. But check this out. For every 1 mole of your salt, right, so here's 1 mole of the salt, I get 1 mole of magnesium ions and 1 mole of sulfate ions. So every time I allow 1 mole, theoretically, 1 mole of that salt to dissociate in a kilogram of water, I end up with 2 moles of ions. What if I were to take a totally different salt and allow that to dissociate in water? Now you have a sample of water, and you have, and it's pure, there's nothing in it yet, and you have its normal boiling point, right? And then you dump a mole of that particular salt, magnesium sulfate, in there. When it dissociates, theoretically, we get 2 moles of ions, and those 2 moles of ions are going to affect the physical property of the water, right? So if the water is trying to escape the liquid phase and enter the gas phase, it's got to move around those ions. It's also tied up with ion-dipole interactions. So 2 moles of ions is going to affect, right, the boiling point or the freezing point of the water. What if, though, I have a totally different salt and it doesn't dissociate to give me 2 moles of ions? What if, for example, I take something like, say, sodium phosphate. So sodium typically has a positive 1 charge. Phosphate has a negative 3 charge. So I'm going to need 3 sodium ions to balance out 1 phosphate. And this will be our solid. And again, we're going to put this into a kilogram of water. So 1 mole of sodium phosphate and what I get on the other side, 3 moles of sodium ions and 1 mole of the phosphate. But check this out. So what do I have here? I have 3 moles of sodium ions, 1 mole of phosphate. So in a kilogram of water, now instead of magnesium sulfate dissociating theoretically to give me 2 moles of ions, I've got 1 mole of sodium phosphate dissociating to give me 4 moles of ions. So you can imagine now that kilogram of water, you want to boil it, you're probably going to need a little bit more energy, right? Because now we've got ion-dipole interactions between the water and 4 moles of ions, right? If I want to freeze the water, I'm going to have to, if that's the temperature at which that particular solution is going to freeze is going to be much lower, right? I need to lower the temperature of that solution because I've got more moles of ions floating around in the mixture. So in these cases, it's helpful to have a way of expressing concentration that's a little bit different than molarity, right? There's moles per liter of solution, because when I'm measuring the heat of a solvent, or when I'm measuring the heat of a solution, the mass of the solvent is the thing that actually is used to determine that heat of solution. So it's nice to have a way of expressing concentration that speaks to the mass of the solvent relative to the moles of things, ions, whatever, molecules actually dissolved in it. We have some other ways of expressing concentration that might seem a little bit more familiar to you. Molality is not exactly like rolling off of everybody's, brain. We use it very specifically for certain calculations, but things like percent by mass or percent by volume might seem just a little bit more familiar. So I have a couple of examples here. And the percent by mass I'm starting with first. It's simply just the mass of the solute divided by the mass of the total solution. And then if you multiply it by 100, then you get a percent by mass, right? So for example, we could have a 25 gram sample of apple cider vinegar. And we're told that contains 6.2% by mass. So that M over M means by mass, acetic acid. So vinegar has acetic acid in it. Vinegar is not just acetic acid, right? But it contains acetic acid. And depending on the vinegar that you have, the percent by mass can vary. Well, I looked up apple cider vinegar and I found that the one that I looked up anyway said 6.2% by mass acetic acid. So the vinegar is the solution and the acetic acid is just a component. It's one of the solutes actually in that solution, right? So what they're telling you is that the entire solution is 6.2% by mass, so M over M, and that actually equals the mass, so this is the mass of the solute, in this case the acetic acid, so this is CH3, CO2H, so that's going to be the formula for acetic acid. We're going to divide this by the mass of the solution, and they give that to us. It's 25 grams of solution. The solution is the vinegar. Here's your solution. And if we multiply that quotient by 100, we end up getting that 6.2%, right? So if we want to figure out what the mass of the solute is, well, we can divide both sides by 100 and then multiply the other side by 25, right? So I'm moving everything on over to the other side and I'm isolating just the mass of the acetic acid. So essentially, what do I have? I've got 25 grams and I'm going to multiply that by 0.062. Right, I'm dividing both sides by 100, and then I'm going to multiply the other side by 25, just to isolate the mass of the acetic acid. So what I get is, now I've got 25 and then 0.062. So I have two sig figs that I'm allowed, but when I do this out, I actually get 1.55 grams. So I'm going to round that up, and so that's going to be the mass of the acetic acid. And that's essentially, with two sig figs, 1.6 grams. So if you have 25 grams of apple cider vinegar and the concentration of acetic acid as a percent by mass, if it's 6.2%, it means that in that 25 gram sample of apple cider vinegar, you have 1.6 grams of acetic acid. We can do the same thing with a percent by volume. Very often when you go out to buy like a bottle of wine or some beer or whatever, they'll tell you the percent by volume of alcohol, and that's ethanol, actually in the solution. The solution is the beer or the wine. The alcohol is not the total solution, right? It's like you're not buying a bottle of pure alcohol, ethanol. You're buying a solution. You're buying a bottle of wine. So in this next example, I have a 750 milliliter bottle of Chianti, and on the label it says that it has 12% by volume alcohol content. So that's telling you that in that 750 milliliter bottle of wine, 12% of that solution is ethanol. So we can set this up the same way to figure out how many milliliters of ethanol, and the 750 milliliters is a standard bottle of wine, right? So 12% of that solution is ethanol. So how many, you can say, X milliliters of ethanol. There's all kinds of alcohols out there. This is the one that is in alcoholic drinks. We're not drinking any other kind of alcohol. And the volume of the solution is the wine. The bottle holds 750 mils. So if I want to figure out the volume of just the alcohol in that bottle of wine, then I'm going to divide both sides by 100, and then I'm going to multiply the other side by 750. That isolates the milliliters of just the ethanol, right? So what I get is essentially 750 milliliters times 0.12. And that will be the volume of the alcohol in that solution, if it's expressed as a percent by volume. This works out to be, and so now what do I have here? 2 sig figs. So I could write 90, right? But if I wrote 90, that would just be 1 sig fig. So if you want to be super anal about it, you can go 9.0 times 10 to the first. Now I know I have 2 sig figs. But if you're just doing this calculation because you're curious, that bottle of wine, if it has a 12% by volume alcohol content, it means that in that entire bottle, 750 milliliters of Chianti, there are 90 milliliters of ethanol. So that's what that means. And then there's another one that people might be familiar with. If you've ever done any sort of like a dissection in a biology lab, and they use formalin, right? So it's formaldehyde, which is a gas at room temperature. It's soluble in water, and they will dissolve the formaldehyde into the water, but they'll present it to you on the bottle. So you have a solution, right? It looks like, a lot of people think formaldehyde's a liquid. It's actually a gas. What you're looking at is formaldehyde dissolved in water. And on the label, it will tell you this is a 37% mass to volume ratio. You see that? M over V. So it's telling you the mass of the solute, in this case, that would be the formaldehyde, per volume of solution. So if I've got a 37% mass to volume aqueous solution of formaldehyde, right, otherwise known as formalin, then what would be the actual mass of the formaldehyde in that particular solution? So we typically have a 100 milliliter sample. If I write down that percent mass to volume, and I want to figure out what the mass of the formaldehyde is, in the solution, and say we have 100 milliliters of it. I think this problem I forgot to write down the volume of the solution. Imagine we have 100 milliliters. We'll just keep it easy. So multiply that by 100. Then the mass of the formaldehyde alone, not the formalin, that's the solution, is going to be 37 grams. Does that make sense? So those are just some other pretty standard ways of expressing the concentration of a solution. I want to move on and start talking about the types of aqueous solutions, and let's get into solubility rules. So your book has a whole chart of these solubility rules. You are going to have to learn these because it's going to be your job to figure out what is soluble in a solution and in a reaction equation and what is going to precipitate. So first, what I want to do is just introduce some types of aqueous solutions. So substances that share similar intermolecular forces have a tendency to dissolve in one another. And we've already covered intermolecular forces, right? We know that things that only have dispersion forces, so typically non-polar solutes, are not going to be soluble. You don't expect them to dissolve in something like water, where there's hydrogen bonding, dipole-dipole interactions, and also dispersion forces. So things that have similar intermolecular forces tend to dissolve in one another. They'll commingle, right? They'll coexist with each other. And the term like dissolves like sort of falls out of that. The like that they're talking about speaks to the intermolecular forces. So for example, I can draw out a salt like, let me just draw a water molecule first. So I've got a water molecule. I'm going to draw it on its side just to help us see. I've got a partial negative charge up by that oxygen, and down between the two hydrogens, I have the center of partial positive charge, right? We have a big giant dipole moment shooting up straight through that water molecule. Along comes, say, some potassium chloride. So the potassium ion is going to have a positive charge. We're going to create an ion dipole interaction between the potassium cation, right, and that partial negative charge up above that oxygen, and then an ion dipole interaction between the chloride anion and that center of partial positive charge between the two hydrogens. I can take another molecule that's pretty similar in this regard. I can take water, for example, and again with the partial negative charge up above the oxygen and the center of partial positive charge between those two hydrogens. And I don't have to have a salt. I can have another molecular compound, like for example, say methanol. There's a partial positive charge, not a huge one, but there's a dipole moment there in that polar covalent bond, and we're going to create a hydrogen bond, right, between the lone pairs of electrons on the oxygen and that partially positive hydrogen atom. And so typically, if you've got an organic molecule that doesn't have a huge amount of hydrocarbon character, meaning I don't have a big, large amount of sort of relatively non-polar character. So typically organic compounds with, say, 6 carbons or less, if they've got the ability to hydrogen bond or they've got this polar covalent bond, we can coordinate with the water molecule, and you'd expect those particular organic compounds to be water soluble. So again, like dissolves like, right? What happens when we take a solute and put it into solution? So say we're going to take a molecule or an ionic compound and we're going to dissolve it or allow it to dissociate in water. What happens if out the other end you end up with a species, your product, that has charge associated with it? This is a very specific type of aqueous solution. It's called an electrolytic solution. So there's a couple of different ways that we can talk about this. The first and easiest way is to simply just take a salt, right, an ionic compound, and if it does have the ability to dissociate, so the lattice energy is not too great, if it has the ability to dissociate, it is water soluble, in other words, then what's going to happen is when that ionic compound dissociates in water, we're going to end up with a mixture, an aqueous mixture of ions. If you have an aqueous mixture of ions, you can conduct electricity through it, right? an electrolytic solution, because electricity is simply just a stream of negative charge, right? It's a stream of electrons. So we can conduct electricity through a solution of charged particles because our electricity is a stream of charged particles. We can also conduct electricity through a stream of charged particles if we simply just melted the salt, right? If you're going to melt the salt, if you have a molten salt, you've separated the ions. So you can conduct electricity through a molten sample of a salt. You cannot conduct electricity through a solid crystal, right? Because we haven't separated the ions. So you need these to be in solution. So these electrolytic solutions are pretty special. And our first example will involve simply just an ionic compound that's going to dissociate. So we can take, I don't know, like sodium hydroxide. That is a solid at room temperature. And it's a metal hydroxide. So we haven't gotten into acid-base chemistry yet, but group 1 metal hydroxides are pretty strong bases, meaning this is going to dissociate completely in the water. And what you get is sodium ions, aqueous, and hydroxide ions, also aqueous. Our product is a sea of charged particles through which we can conduct a stream of charged particles, otherwise known as electricity. So we have an electrolytic solution here. What if I had another kind of a salt? What if I took, like, say, potassium sulfate? So K2SO4, solid. What if I decided to dissolve that into a glass of water? What do I get? Well, I'm going to get 2 moles of the potassium ion and 1 mole of sulfate, all in solution. Here's the deal. The more ions you have in solution, the greater the conductivity of that solution. So if I've got a lot of ions in solution, for example, for every 1 mole of sodium hydroxide, I theoretically will generate 2 moles of ions. For every 1 mole of potassium sulfate, theoretically, I generate, if it dissociates completely, right, 3 moles of ions in solution. The more ions you have in solution, the greater the conductivity. So the greater number of ions will give you greater conductivity. Do you have to always have a salt, right, or an ionic compound to generate an electrolytic solution? Nope. So again, we haven't covered acid-base chemistry yet, but I'm going to give you a quick example right now of a situation where you can take a molecular compound and allow it to react with water, not just dissolve, but then also react with water, and the product that you get has charge. So if the product that you create is a solution of charged particles, then yeah, you can also conduct electricity through that. You can conduct electricity through vinegar solution, right? It's an aqueous solution of, well, depending on the vinegar you're talking about, but if it's acetic acid, which is a weak acid, right, we're going to create some charged particles. We're going to protonate the water with the acid. So you can conduct electricity through a solution of vinegar. You can take something like ammonia, which is a gas at room temperature. And it's a weak base, meaning it does not 100% dissociate. So that's what that little arrow means right there. At any given moment, you have some ammonia gas, and any other given moment, we have taken a hydrogen off of the water, and we make the ammonium ion, which will be in solution, so aqueous, we have deprotonated the water. Now, who did this? It was the ammonia. Remember, ammonia has these lone pairs of electrons on the nitrogen. Those lone pairs of electrons are going to steal a hydrogen off of the water molecule and then deposit those electrons right from that covalent bond back onto the oxygen. So the hydroxide anion has a negative charge, and the ammonium ion has a positive 1 charge. We have an aqueous solution of charged particles. This is also an electrolytic solution. What if I took like an acid, right? If I took a strong acid, for example, and you can have a weak acid, that's fine, but hydrogen chloride is going to be a gas at room temperature. And later we'll see that this is a strong acid, so this completely dissociates in water. What do you get though? Well, I get some protonated water, right? So the water also has lone pairs of electrons. It's going to take that partially positive hydrogen off of the hydrogen chloride because there's that dipole moment, right? The chlorine is hogging the electron density. So it's a polar covalent bond, puts a partial positive charge on the hydrogen. And we're going to protonate the water, and then we end up with the chloride anion. But our solution has charged particles, so it is an electrolytic solution. You can conduct electricity through this particular solution of charged particles. So you don't have to always have ionic compounds to make electrolytic solutions. You simply just have to have charged particles in that aqueous solution. What happens if you have a molecular compound that is simply just going to dissolve in the water? And the particles that you get, the product that you get anyway, out the other side, don't have any charge. Because not all water-soluble molecules are going to yield a charged product, right? So for example, what if I were to take, say, table sugar, sucrose, right? And I'll just use the molecular formula for this because sucrose is kind of takes up some space. So table sugar, and this is going to be put into a glass of water. It's not wildly soluble in water at room temperature, but it is soluble, right? What do I get out the other side? Well, I'm simply just going to get some wet sugar, right? But there's no charge on that particular species. So this molecule is going to be water soluble due to all of the, if I had drawn out the structure, you'd see all the hydroxyl groups that can hydrogen bond, dipole-dipole interactions, you name it. They're all in here, and so they're water soluble, but not going to create a charged solution on the other side. So this is called a non-electrolyte. What else can we draw for you to show this? So this might be, this is going to be a tough one. I'm just going to do ethanol. So alcohols are very weak acids. And so, you might barely be able to conduct a little electricity through this, but probably not much. It is water soluble. So the alcohol itself is very weakly acidic, so there's a tiny chance that you're going to protonate that water molecule, but by and large, what you actually get out the other side is simply just ethanol that has dissolved. And so for the most part, this is going to be non-electrolytic. So how do I know what dissolves and what doesn't dissolve? Because I'm sitting here saying, oh, the HCl is going to dissolve all the way. The ammonia is going to partially dissociate. It will be soluble, but, we went back and we were talking about sodium hydroxide, and I said that's 100% soluble in water. What about something like silver chloride? When we were talking about the types of reactions in chapter 7, and I said silver chloride is an ionic compound and it is not water soluble. Like, how did I just know that? So we've got these rules that we have typically in based 100% on experimental data, right, for predicting the solubility of an ionic compound in solution. So it's just a list of rules helping you sort of navigate like what is soluble and what's not soluble. And so there are some compounds that are 100% soluble in water at room temperature with no exception at all. So down here in this little chart, we have a whole pile of ions where if I had anything ionically coordinated with a lithium, sodium, potassium, or ammonium ion, it would be soluble in general, with no exceptions. If I've got a nitrate or an acetate, I've got a soluble compound with no exceptions. If I've got a chloride, a bromide, or an iodide, the compound will generally be soluble except when it's paired with silver, mercury, or lead ions. And so all of this stuff is listed in this little chart over here. So you see all these exceptions on this side over here. Your compound will be soluble with those exceptions, with either no exception at all or, for example, generally all sulfates are soluble, except when it pairs with those group 2 ions that are listed there, silver or lead 2+. And then you'll get a precipitate. The resulting compound is insoluble. They're telling you that particular compound will not be soluble. So for example, I can write out like lithium hydroxide. I see here that, for example, in my chart, I see that all compounds where the lithium +1 cation is involved are soluble without exception. I also look down the bottom of the chart and I see that hydroxides and sulfides are generally insoluble, but then I look over at the exceptions and it says, hey, but except when it's paired up with these. Notice how those, lithium, sodium, potassium, or the ammonium ion, are always soluble without exception. So the exception to the rule for the insolubility of the hydroxide or the sulfide are going to be those cations where there aren't any insoluble exceptions. So this thing right here will give us lithium +1 aqueous plus hydroxide aqueous, right? What if I were to pair up that hydroxide with something else? Like, for example, let's see. How about magnesium? So hydroxide typically will have a -1 charge. Magnesium takes on a +2 charge. And so I look over at my chart and I don't see magnesium listed on the without exception rule for any of the soluble stuff. I look down and I see hydroxides are generally insoluble. And I look over and I see the exceptions. Well, they'll be soluble when they're paired up with lithium, sodium, potassium, or ammonium. And then they separate the sulfide and the hydroxide. And the hydroxide is generally insoluble unless it's paired up with a group 1 metal or the ammonium cation, or also if it's paired up with calcium, strontium, or barium. And those compounds are only going to be slightly soluble. In Chem 32, you will actually do calculations to figure out how much of that salt actually will go into solution. But if I take magnesium hydroxide, and I don't see magnesium listed as any sort of an exception, and I put this into some water, I get plus water. And so I'm basically staring at precipitate, right? it hasn't precipitated from solution. It just hasn't actually dissolved. So I'm staring at a solid, right? It's just not soluble at all. So let's talk about these precipitation reactions, right? We have an idea of what's soluble and not soluble, right? Theoretically, based on those experimental data. We can actually draw out these precipitation reactions based on the information that we're given. So I have 3 examples here. First one is an aqueous solution of silver nitrate is allowed to react with an aqueous solution of sodium chloride. So they're telling you everything that you need to know about this particular reaction, right? They tell you that an aqueous solution of silver nitrate, an aqueous solution tells you this thing is dissolved. So I can go ahead and I can write out silver nitrate. And we know from our solubility chart that all nitrates are soluble in water at room temperature without exception. To this, we're going to add an aqueous solution of sodium chloride. Sodium is a group 1 ion, right? So without exception, those are all soluble. Now, when this is allowed to react, I'm going to use my solubility rules to predict what is going to be in solution, right, on the product side, and what is going to precipitate. In other words, what solid is going to crash out of solution. So when I do this reaction in chapter 7, we talked about this as a double replacement reaction. And we said, we're just going to swap dance partners here. We've got sodium is going to swap dance partners with silver. So instead of sodium dancing with... Hey guys, so we're going to start chapter 8.